All right, so we've looked at how to find the interval of convergence for a series, but I've just basically handed you these series without really much explanation of what they're supposed to be representing. So let's take a look at examples in this video where we can actually use power series to represent a particular function that may be of interest to us. All right, and believe it or not, the first one is one that you've seen before. If you think about your geometric series, we said the sum of r to the n would, well, if we set the constant c equal to 1, that converges to 1 over 1 minus r, right? And if you replace r with x, think of it as a variable, then we get a formula that says the following. The sum of x to the n is equal to 1 over 1 minus x. So we can use a series as a representation for this function. All right, let's go to Desmos and actually compare what these series look like. We'll plot 1 over 1 minus x, then we'll plot a partial series and see how they compare. All right, so here we go. We've got our 1 over 1 minus x in black, and you notice it is just a hyperbola here. We've got a vertical asymptote at x equals 1, of course, because we're dividing by 0 there. And if I add my partial sums here, I'm going to add, first of all, just the linear approximation. You see that what we get is what looks like a tangent line at x equals 0. And as I add more terms in my sum, so I'm not adding up all the powers of x to the n, but just the first couple, now I've got a parabola, now I've got a cubic, quartic, and so on. And as I add more, okay, now I've got 40 terms. It looks like the partial sums are very, very, very close to the hyperbola over some range, but they don't match it everywhere, right? Somewhere around here, maybe around -1, suddenly these partial sums have nothing to do with the hyperbola. And in fact, I could keep going here. Let me go out to 100. And notice it doesn't make it any better. Even if I add up 100 terms, it doesn't seem like I'm actually approximating things any better than I was before. And in the positive end, it looks like everything works great up until that vertical asymptote. But beyond that, we're not really getting this other part of the hyperbola well. So I actually lied to you a moment ago. I said that these two things were the same, but they're not the same. They are only the same when the sum converges. This sum on the left-hand side doesn't always converge. It doesn't converge for all values of x. In fact, it only converges for a narrow range of x values. And let's actually compute that interval of convergence. So if we applied our ratio test, we would have the limit as n goes to infinity of x to the n plus 1 all over, I guess that's the n plus first term. And if we divide that by the previous term, we'll have just x to the n, which would mean we'd be left with just absolute value of x. And that only converges if this is less than 1. Aha! So if we go back to our picture, the reason that our series representation only behaved like the curve for this narrow range is because that was the interval from -1 to 1. That's the only place that the series converges. And this polynomial that we're writing down diverges for all values of x outside of that range. And this is not something we'll make rigorous right now, but you might suspect that the reason that this diverges outside of the narrow range from -1 to 1 is due to this asymptote, right? If you think about trying to represent a function that goes off to infinity, it has to get really, 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 really steep to do that. And in doing so, if you add up something that's really, really steep, polynomials don't just change their slope instantly. And so to try to represent the rest of the function is really impossible if you try to get this asymptote correct. Okay, so that's just a very hand-wavy justification for why this only converges from -1 to 1. We have a power series centered at 0, and we are able to go 1 unit before we run into an asymptote. But once we hit the asymptote, our approximation can't possibly hope to be successful. And again, that's due to the fact that we have a function that's going off to infinity, and we're trying to represent it by these nice continuous polynomials. Okay, so we can represent the function 1 over 1 minus x as a power series over a narrow range. And once we've got that function represented, we can actually start to represent some other functions. All right, so for example, suppose we wanted to represent this function as a power series. How would we do that? Well, notice that's the same thing as 1 over 1 minus x squared. And if I were to plug that negative x squared into my power series above, that should give me a series for my new function. So this should be equal to the sum from n equals 0 to infinity of minus x squared to the n. So all I'm doing is I'm just plugging right into there and replacing x with negative x squared on both the left and the right hand side. And we could simplify that to, we could write that as negative 1 raised to the n times x to the 2n. And there we go, we've got a power series for 1 over 1 plus x squared. All right, so now you're maybe starting to see that we can actually use this geometric series to build all kinds of power series. So for example, let's find a power series for the arctangent of x. You say, wait a minute, what does that have to do with anything? Well, remember, the arctangent is the antiderivative of 1 over 1 plus x squared. And so if we take our series representation for 1 over 1 plus x squared, we will get the integral of the sum of n equals 0 to infinity, negative 1 to the n times x to the 2n, all dx. And now I'm going to make an assumption here, but this is an assumption that we should really think about before we just trust it blindly. I'm going to assume that we can interchange the order. We have a sum inside of the integral that we can break that up into a sum of integrals like we would for any sort of finite sum. But as you remember, earlier in the semester, we've seen that sometimes assuming that the things that work well for finite things works well for the infinite is not always correct, right? That's not always a safe assumption. And so we're going to need to justify that in just a moment. All right, so I'm going to interchange the order. Instead of an integral of sums, I'm going to turn it into a sum of integrals. All right, and so we've got the integral of what's inside. And notice negative 1 to the n doesn't have any x's in it, so I could pull that out as well. And so I'll just have the integral of x to the 2n dx. And that is just the power of x, and so its antiderivative is going to involve increasing the power by 1, and then, of course, dividing by a constant. And there we go. We've got a power series for the arctangent function, and we can even write down the first few terms just to get a sense of what that does. When n equals 0, we have negative 1 to the 0, x to the 0 plus 1 over 0 plus 1, so that's just going to be x, minus the next term. We plug in 1, we'll have negative 1 to the 1, there's the minus sign, times x to the 2 plus 1, so x cubed, all over 2 plus 1. And then the next one would be x to the 5th over 5 and x to the 7th over 7. And you can see there's a nice pattern there. And that's going to go on forever. Okay, so there's the arctangent function written as a power series. It is a power series centered at 0. And let me just quickly justify this step for you where we interchange the sum and the integral. And it's going to involve a theorem from our textbook, which says the following, that the term-by-term differentiation integration, suppose we have a power series that has radius of convergence r greater than 0, then the power series is differentiable, meaning we can take derivatives of it from negative r, c minus r to c plus r, or for all x if the radius is infinite. And we can also integrate and differentiate term by term, which means when we integrate it, we can just take the integral of each term in the sum from that point. Okay? And these series have the same radius of convergence. The interval might be different. The endpoints may change whether they converge or diverge, but they'll converge on the same interval. So what does that have to do with this problem? Well, if we go back to our analysis, we assumed that it was okay to integrate term by term, but that's only true at values of x where this series converges. So we need to know where does this series converge to know whether that's actually going to be correct. So let's find the radius and interval of convergence for the sum of minus 1 to the n, x to the 2n plus 1 over 2n plus 1 from n equals 0 to infinity. And so we'll apply our ratio test. We're going to have the limit as n goes to infinity of the next term. So I'll plug in n plus 1 there. So x to the 2 times n plus 1 plus 1, all over 2 times n plus 1 plus 1, times the reciprocal of the nth term. So 2n plus 1, all over minus 1 to the n, x to the 2n plus 1. And we can simplify a little bit. We'll cancel out some factors of negative 1. Notice this is just 2n plus 3 when we multiply out, which means we're going to cancel all 2n plus 1, and then we'll have 2 extra factors of x on top. And this is just going to be 2n plus 3 as well. So we will have the limit as n goes to infinity of minus 1 times x squared times 2n plus 1 all over 2n plus 3. And when we take an absolute value, the minus 1 will go away. We'll be left with just x squared times the limit as n goes to infinity of 2n plus 1 over 2n plus 3. And you can easily show that that is going to be equal to 1. And so we get just x squared, or yeah, that's fine. So rho is equal to x squared. Well, when does that converge? Well, it converges when that is less than 1, and x squared is less than 1 when x is between negative 1 and 1. Okay? So interesting. Our interval of convergence, now we did not check the endpoints, we could, but at least the radius of convergence here is 1, which is exactly the same as the original problem, and then this 1 over 1 plus x squared, which we derived from it. And that is maybe a little bit surprising, but that's exactly what the theorem said. It said that we can do this differentiation and integration term by term, but only over the interval of convergence, or only over the range where the series converges. And to show why that's a little bit surprising, we can look at the graph. So let me change this function here. Instead of 1 over 1 minus x, let's graph arctangent of x. Okay, so there's the arctangent of x. And now I'm going to plot my power series, which we said was negative 1 to the n times x to the 2n plus 1 doesn't want to let me do that, over 2n plus 1. Okay, and as we add more and more terms, we see that this does seem to hug the arctangent function, but it only does so over a narrow range from negative 1 to 1. But unlike the original function, 1 over 1 minus x, there's no asymptotes here. There's no asymptotes in arctangent of x, at least no vertical asymptotes. There's horizontal asymptotes. But for some reason, it's still breaking down at negative 1 and 1. And so I think this is kind of surprising. It's almost like the asymptote at 1 over 1 minus x somehow caused changes of behavior here in this other function, arctangent of x, because of the fact that their power series are very much tied to each other. So we would say that we can represent arctangent of x with the power series displayed here, but that only is going to give us the correct answers for a range between negative 1 and 1. Outside of that range, it's going to diverge. Okay, so we don't have to stop there. There are a whole variety of different power series that we could derive from the geometric series, but that's not necessarily going to be enough to describe any possible function that we would want, at least not easily. And so in the next video, we'll see how we can start to construct power series using a different approach without these sort of clever manipulations of the geometric series.